Okay, so the meeting's now being recorded.
Fantastic. If I just say a few words before we begin. Well, on behalf of the Cancer Centre Oxford team, I'd like to thank everyone for joining again. Further to the great feedback we had from the first session, we wanted to expand into the intermediate level training today, and then in the next couple of weeks into an advanced level training session. I hope this session is useful for everyone, just as the first one. And I wanted to thank you, Sean, and your team in advance for arranging the training. If anyone has any questions, please get in touch with myself. My name is Marlon Isais. I'm happy to help anyone who'd like to access Halo from our end. And I'll leave it with you, Sean, to take away.
Thanks very much. Okay, so welcome everyone to the intermediate training. And I hope you all were able to have a little play with Halo following on from the basic overview we did a couple of weeks ago. You're all currently on mute, but if you want to add questions or comments, then just please either unmute yourself and make some addition to the conversation. I would ask if Esther could please mute herself, just because I can hear some feedback. Thank you very much. That seems to be a lot better. No, there's Banu, could you also mute yourself, please? Thank you very much. Okay, so yeah, as I was saying, if there's any comments or questions, then please just unmute yourself and jump on in. We've got 1.5 hours, possibly two hours today, but we've got a lot to get through. So we'll press on. We'll see how much we can get done. So we're looking at some of the nuclear segmentation algorithms, identifying cells, and then applying thresholds. Those are multiplex IHC, high-plex fluorescence, the RNA-scope type of analysis, and some of the basic analysis like area detection or stain positive pixel counts. That's almost the easy bit. We're going to dive into something which is a little bit more technical, which is the AI tissue classification, which was requested. And we're going to do TMAs, which is the segmentation of a whole slide image into individual TMA cores. So the most part of this training will be me doing the presentation. I might rely on my colleagues, Natasha or Ghislaine, for some images if I don't have them. But most of the part it will be me leading the presentations. Okay, so as with the training we had last time, we're going to do a screen share of the software itself, just so we can get the immersed really in what we're doing. I've just remembered there's also a chat window, so because there's so many of you on here, if you don't want to interrupt or voice a question in front of so many people, then you can add it to the chat. And I'll try and treat this a bit like a webinar and keep checking the chat to see if there's any commentary. Okay, so let's just use WebEx to share content. I'm going to share the Halo software. So you now should be able to see a grey and orange interface, which says Halo 3.1 at the top. Welcome, Philip, to the meeting. Okay, so what we'll do is we'll just take a quick recap to where we were last time. Remember, there is
everyone to put themselves on mute because there's some interruption in the background.
Yeah, thank you. That's a very good point. If you look down the participants list, you'll be able to see a little blue sound icon from the not the presenter, the attendee that's got feedback. You should just see the blue speaking icon next to my name.
As a host, Sean, you can also mute everyone.
That's a good point. Might have to stop sharing to do that. Let's just sorry everybody, but I'm going to just run down and mute everybody. Should be good to go. Okay, so we're back in the Halo screen. Yeah, last time we talked about the basic workflow of the software. So we came from the Studies tab where we open images into the main viewer just by double-clicking on the icon. Sorting, searching for images is all done here. And this was something we covered in more detail last time. We skipped over the TMA tab last time, but we're going to study that further this time. The annotations tab we looked at a little bit, and as a reminder, that is the options down here. So you've got the brush tool, the pen tool, all of these flood annotators and shapes. These are ways that you annotate the image. Now the classifiers tab would have been touched on last time, but we didn't look at any of the AI-based classifiers. So this time we'll probably take a look at AI-based tissue classification. You'll notice that with Halo 3.1, some new options have appeared down here for nuclear segmentation and also phenotyping of cells. That is really exciting and new and powerful, but there's a certain risk with overloading of information all at once. So it might be better to just focus on tissue classification first, and then when people have got more of a basics of these two networks for tissue classification, we can move on. Or we could do ad hoc training sessions for these type of networks. Then we came on to the analysis, and we would have done some kind of basic analysis last time. Typically, it's the multiplex IHC module or area quantification cytonuclear. One of these ones is usually used first for the initial training. But as you can see, there's a lot more modules that we could pick depending on our application requirement. And finally, we looked at the results tab where you can view results from whole slide image analysis, and you can also look at object data. So that's individual cells or other objects like vessels, plaques, things like that. Okay, so I hope you all had a play with Halo based on the conversations we had a couple of weeks ago. So this time I'm going to cover a few of the topics under the title Intermediate Training. So this training will assume that you've already got a little bit of a basic understanding of the software. It's okay if you don't, because all of the training that we offer at Indica is unlimited, so we can always come back and revisit. This can be done individually or en masse, as you prefer. Okay, so I'm going to start with a TMA, and what we'll do is we'll imagine you had a whole slide image of a TMA, which you opened and were now viewing in the software. And so here you can see a few examples of TMAs that I've opened in Halo. I think I might have mentioned this before, but when you're doing a TMA type analysis, it's usually beneficial to work up an analysis algorithm that you want to run on the TMA before you segment it. And this is because if I optimize algorithm settings, you want to try and optimize them across multiple TMA cores. So obviously the TMA has some variability across it, being different individual cores. So you want to try and optimize settings across the TMA prior to segmentation. You can see here some differences in staining intensity, background, the nuclear morphology. You'll see differences across the array. For that reason, if you are doing TMA analysis, I would recommend as a starting point is to do a area-based assessment of the stain. So that's one of our tasks for today is area detection or area quantification. So we'll loop in this requirement into the TMA overview. So we're going to first do an area detection, so detecting the positive area for each of the stains. So I'll hop over to the analysis tab, And I'll select setting actions, and this is where you're able to load an algorithm from the list of pre-canned algorithms. So we select load. It's going to ask us whether we want to save anything that we've initially done. Select don't save. And if you choose area quantification and hit select, you'll see that this brings up a list of parameters here. Before I move on to that, I should just note that you have a new option here in 3.1, which says show all installed module versions. So if you have multiple occurrences of the same module because we've updated you, you can view them all here. And you'll see here I've got 2 versions of Hyplex. But if you want a cleaner looking list and you want to be drawn just to the most recent and therefore least bugs, most advanced functions module, then just leave that unchecked. And when new users come to the software, and I would probably suspect that there'll be a lot of new users here based on the number of attendees. Leave this unchecked so that new users then come along to use the most recent versions. It'd only be if you had a requirement for consistency with a legacy version of the module that you would probably check this. So let's select area quant and hit the button down here to open the module. And you'll see that a very basic module opens up in front of us. And with all of our modules and classifiers, the first step is to select Analyze and open the real-time tuning window. So if this option pops up, just select OK and type in manually the value for microns per pixel. Now, if you have lots of images that you're loading into the software that don't have the image resolution set, usually they'll be set in the metadata, then you can import this value in batch across all of the images at once. There is a method to do that, so you won't have to do it individually. Okay, so what we've can see now is the real-time tuning window has popped up, and what we term the markup image has appeared over the input image or the section that we've captured using the Apereo scanner. What we've got is a colored overlay, and the most intense staining is represented by the red, and then going down to orange for moderate, and then further down to yellow for weak positive, and then the transparent area is classed as negative for the stain of interest. So this won't look perfect straight away, so you'll need to do some minor optimization. So as with all the modules, you start with the pre-canned settings. You've got a blue for hematoxin and a brown for DAB here, but you may want to repick the stains from the image. And in some of the modules that we'll look at later today, we'll be doing some repicking with a lot of channels. But this is a nice place to start because we're just going to pick a couple of stains. So we have the option to go up to 5. We've only got 2 here, the hematoxin and the DAB. So let's choose 2, and stain 1 we can name as hematox. And if we click the little more options icon here, you'll see it brings up this separate window which allows us to select stain from the image. So let's use the pixel zoom slider and just zoom in like so. You can move around using the tabs, and when you're ready, press OK. I'm not quite there yet. You see I've come off the edge of the nucleus. So press OK. What happens when you tell Halo what to look for? Of course, the input image updates because it's now detecting more accurately the stain that is representative of the actual input of your image. It's not using default values. Let's pick a second stain. Similar process to before. Okay, so now Halo is trying to find in this markup the blue for the nuclear stain. And you'll be able to change which markup you wish to appear using this output image drop-down. So I could look at what we think is hematoxylin, what we think is DAB, and then look at the markups respectively. Okay, so there's a co-localized markup. Now, before you move on, it would be prudent just to set some thresholds here. So I'll select the hematoxylin markup to start with, and you'll see here that I've got the option down here under hematoxylin, just to change the sliders. So if I move these across towards the right, you'll see that less of the tissue becomes positive. Could have these much further out if you wanted to. So Halo will report area of positivity and the individual breakdown of these thresholds. So you don't need to worry about there being information on whether there's negative and all positivities combined. We get that anyway. For DAB, just change to the DAB stain and then check that looks okay where you expect it to be. And then DAB markup. And the same process then applies. A little bit more realistic that you would do it on this large area of staining. Try and make sure you don't have too much background. And this is the time to visit multiple cores because you don't want to optimize just on one core and then have less than perfect segmentation on a core that is much further along. So this is a nice example, actually, some negative cores that we just need to scan over. Here we've got some more moderate staining. Okay, great. What you can do now is, if you wished, look at the co-localization markup, and it's possible to change these colors. So if you wanted it to be brown and blue on the markup, those colors now best represent the input stains. Some people like to have the markup overlaid in the same color, and other people prefer to have a totally different color, so that when you view the transparency down here, you get a clear indication, you're not having two overlapping colors. So some people like to go for totally different. So have the nuclei in pink and this in cyan. Okay, so down under advanced, there's one last thing to do. And let's put the markup, say, for DAB active. Turn this on. And what we're going to do under advanced is just add a little bit of blur, just so any little speckles are blurred out. So you see, if we increase this, we can just blur. Arguably, this is just for aesthetic reasons, really, for your markup images. The other thing which you'll notice is that you see here there's a black outline around the TMA core. That's because of something called minimum tissue edge optical density. So most of the bright field modules operate this parameter, and it's effectively telling Halo what is the glass slide and what is your tissue. The only image format I'd be a little bit wary of this at default settings is the Zeiss CZI format, which tends to have a little bit of a darker background, and you'll need to adjust this, usually adjust it upwards. Most other formats, you can leave it on the standard setting. So because we're doing an area-based assessment, this is very important, because if we know the total area of the tissue, we can get an accurate percentage of positive stained tissue. If this is wrong, and I'll deliberately make it incorrect here. See, let's increase. There, this is now counted as tissue. if I increase this setting again, you can see how the black line is now gradually coming towards the. If I increase it too high, now this area is counted as glass. So let's drop it down back to standard. Okay, if you want to, you can also use a tissue edge thickness. So you'll see how that retracts slightly. There are certain occasions where this might be utilized. So for example, if you had an intense staining on the side of the tissue, maybe the stain is washed up, you'll find that is often detected as long, high aspect ratio nuclei, which are not really there. So if you do have some kind of staining artifact, then you can increase tissue edge thickness. So we're pulling the marker just a little bit back from the actual edge of the tissue. I don't think I'll do that in this case. I think it's unnecessary. You can apply a classifier to any module, so that's possible here. So you can see that we've got some options here to add classifiers. Don't need to do that today, but you can classify across the TMA, and probably best left to the advanced session, but applying an AI classifier would benefit you in terms of a variable data set, of which a TMA usually is. So keep that in mind, that classifiers can be applied across a large tissue microarray. Okay, so really I've just given you a bit of an overview of an area detection module. So what we'll do is it will save these settings now. This is important for the TMA process. So let's just select setting actions and hit save. What will happen is it will give you a default file name, and then I can just add something in here. So we can say now the algorithm is saved to the TMA study folder. And that's something to note as well. When you're looking for things like algorithms and classifiers, they're located in the folders alongside the images. So you don't have this big array of algorithms spread all over the place. They are neatly located in the respective study folders. So let's hit save. This should be quite quick because it's a small module. And now we're ready to do some TMA segmentation. Okay, if there's ever a little bit of a pause, that's probably just me taking a drink of water. Okay, so now what you could do is you could run these algorithms across the whole array, and then you'd have information assessing how much tissue the array is combined and how much of that is positive based on the settings that you've worked up. We want to try and approach this with a little bit more of an elegant solution. So we're going to select the drop down here and scroll down to segment TMA. I mentioned last time that anything in Halo that's accessible from a drop down up top usually has the same options by right clicking, and it's typically just a habit that you form, whether you go for the drop down down here or you just right click on the image you want to analyze. Remember that for any of these operations that multiple things can be selected at once, and you could analyze these in batch if you wanted. Segment TMA is grayed out here because this is a single process, but the other operations you can do in batch. That applies here as well. Okay, so we're going to do one image at a time. So we'll select down to segment TMA. And here you can see some existing blocks that I've generated in the past, but I'm going to go through the process as if no blocks existed. So I'll just delete these existing blocks. And we'll start from scratch. Okay, so the first time you're segmenting a TMA, you've got no blocks that are pre-existing, so you have to select new block. And good morning, Victor. Morning, Victor. Nice to have you
Sean.
here. Hello. So what we'll do is we'll just show you the basic overview of how you could select an area and then align that with the inputs up here. So you can see I've got a very small thumbnail. You can expand that out, but that will show you the structure of the TMA. And what you could do is just drag an area and select add. That was a right-click operation. Just build up a map that best match the input of the TMA. So your TMA should have a defined structure, and you'll be able to recreate this using this mapped overlay, like so. Now, we've got a geometric overlay. The cores or spots don't have any information associated with them. So if you wanted to, you could type in, say this is the control, and then assign that to each core. So the cores could have manual data entry applied to them. That's the slow way of doing things, which we would probably avoid doing in most instances. The exception would be a small TMA. Most of the time we would try and use the import wizard. So let's just remove this data set. So let's select clear, and you can see that when I go back to square one, there's nothing present. So let's select the import wizard, and it's going to ask us to go through a guide that will bring in a TMA block definition from a spreadsheet. This is the wizard. It's the quick way of doing things. If you have the data for your TMA already in a spreadsheet, all you have to do is copy that data to clipboard, and Halo will read that and bring it in and apply it through the wizard. So we have options for geometric layout. And that's basically where, and I'll just come to this Excel document. So you should all be able to see my Excel now as well. Please speak up if you can't see it. But this should show an overview of a TMA array in Excel with cells representing cores. So this is what we call the geometric overlay. And I'm going to just press Control C on the keyboard to copy that information to clipboard. So you can see there that it's copied. Let's go back to Halo itself, and we should all be able to see Halo. I'm still getting shared, shown in green, so please speak up if Halo isn't there, but you should be able to see it. So we've got geometric layout. Let's press next, and this is where it's going to ask you how many cores of information or how many cells worth of information are you going to apply to each core. So in my array, you had only one cell per core. Let's go back to Halo. You notice you could increase this, and this was what it would look like. But typically people just add one core because your Excel will get a little bit confusing if you have multiple cores worth of data. So let's select next. And here's the area copied to clipboard. Highlight the desired section of your spreadsheet and copy it to clipboard. I've already done that, so I don't need to do anything at this stage. I just press next. Notice you don't even have to save the spreadsheet. So if you've got an online, maybe you're opening in SharePoint or something, you don't have to download the spreadsheet or have access to it. All you need to do is open it online, copy the information, and then run through Halo. Okay, so as I press next, then we saw that the overlay appeared, which basically shows us the geometric arrangement of the TMA. And you'll notice that because I copied cells with empty space, they've been represented here, and this will help us later on. Try and array your Excel data with the spacing in place as well. That will really help when we come to align the TMA later on. Currently, there's no information associated. You see that this is empty up here. So what we need to do is we need to press this add button here. So from the drop down, let's select the first cell, and if we select add, you'll see that information pertaining to the naming nomenclature appears in this list. It's also possible to add some information across all of the cells in the array, all of the cores in the array. It's very easy to confuse cells and cores when you're mentioning one and the other 10 times after each other. So I'll just demonstrate. Press the separator icon. I mean, you can change this if you want, so you could put a comma or a forward slash. And then you could put static text, so you could put colon. Just some information that reminds you the tissue type or the treatment or something like that, as well as the information from Excel. If you press clear, you'll go back to square one. If you press undo, you'll undo the last operation, like so. So press next when you're finished. Press next again here because we've only got a single cell of information from Excel. And that's it, really. It says you've successfully completed the wizard. You can edit the TMA block at any time without the wizard. So remember at the start, we saw that we had TMA blocks that were pre-existing. What we've done here is we've gone through the process of creating the TMA block. So if I save this block, it will now appear in our pre-saved blocks list, and we can access it readily without having to go through the import again. So you can imagine if you're creating TMAs with the same arrangement of cores, you can use the same block, and that's going to save you some time. So I'll just call this TMA block, very generic name. Let's press save. And we've now got the TMA block in our list. So I'm going to select it. Okay, so a couple of things have happened. The observant amongst you will notice that we've jumped from studies to TMA, so that happens automatically. And then the very obvious thing that's happened is this has opened another interface called the TMA segmentation alignment. It's a bit of a complicated name, but essentially all you're doing is dragging these points to overlay the cores. I'm going to expand to make it a bit easier to see. So you should be able to see now the whole array. Now, if you had to drag these manually, needless to say, it'd be quite tedious. Luckily, it can be done using this stretching and elastic kind of profile. So as you drag one core, it makes changes across the entire net, shall we say. It behaves a little bit like a net, pulling the other cores into alignment. I would advise you to start at the outer corners first. So something like this. This example is a little bit tricky because you have to check whether these are actually cores with a little bit of data or not. All will become clear as we start working towards the when you've done the outer corners, you can work on the outer middle, for want of a better word, and then start doing the inner corners. It may be that you need to make micro adjustments to individual cores, but you don't need to do this to a high degree of accuracy. It's just to get it close enough so that Halo can take over. Okay, so when you finish that alignment, bear in mind this will be easier if you have a smaller array. You've got some options here. If you wanted to, you could use this to flip or mirror the array. Maybe you've imaged it backwards or put the slide in backwards. Something's gone wrong. You can flip. You can rotate as well if you want to. I don't usually adjust these in the process of demoing this because obviously I know which way the array is going to go. Spot operations. Okay, so this is where you should probably pay more attention. If we look at the size, what we can see is that sliding this up will increase the selection. There's a square and there's also a circle. So let me just explain what each shape does. Everything within the square will be analyzed, and data towards that will be will contribute towards the score or overall data output for that particular core. So just let that remind yourself of that fact. Everything within the square contributes towards the core. So if you go too big on the size, then you'll see that a square may overlap into a neighboring core's tissue, and then you'll have incorrect data. So try and make sure the squares don't overlap, but other than that, have them as large as they can without the overlap. Try and get the individual circles to nicely map around the cores. Okay, so I mean, this is quite nice already. You could probably get good data as it is, but let's just press Auto Center, and we'll let Halo try and improve on what we've done. So it's done a little bit of a neater alignment, where it's jumped to fit the circles around the cores as accurately as it can. The next thing we have to do is an invalid threshold. An invalid basically means to remove the cores that we think don't have enough tissue to be useful for analysis. I mean, there's some obvious ones here, which we could just select out by pressing the I key, like so. So that's me just selecting the core and pressing I. If you don't want to do that manually, then there's an invalid threshold, which as you increase this, you'll just see that more cores become deselected. Obviously, the red cross is demarks them as to be removed from the selection. Invalidate can be done here using this button, and then you've got some options here to unfix. So that will reset the alignment or start over, neither of which you would want to press at this stage. Let's press save, and this is our then alignment completed, and then Halo will jump to the TMA tab, and it will allow us to perform some operations on the now segmented array. Those operations could be to analyze a small number of cores, to analyze all of the cores, or to analyze all of the cores across multiple TMAs. Okay, so here you can see we've got the array. What I've got open in the viewer is still the whole slide image. If I click on one of the cores, you'll see that this then opens a separate image of the TMA core. It's possible to navigate through the array by pressing the spacebar. And this is probably one of the ways you could annotate the array as well. If you wanted to perform annotations, you could do this here by selecting some of the tools, drawing the annotation, and moving on. Here I'm using directional keys just to go up and down, side to side, just studying the cores. If during this viewing of the array you want to add information in manually, then we have a tool for that, and it's called Select Scoring Template. So we'll hit that, and if I create a new template, I could put TMA core score, select new, and then I can have some options of what I want to add in. It could be text, it could be a list of options. So let's change that to score. And let's put in, oops, like so. What I could do here then is just save the template. And if I then select this template, a little window appears down here, and the user can come in and select some options here. You know, you could add custom text or a description of the core. It'll be saved to the database, but instead I can just select it like so. Select a score. Maybe that one will be 1+. Move on to the next one. and that is a scoring template. Please feel free to have a play and make the scoring templates as you see fit. Okay, so other things you could do, you could set stain, which basically adds a description to the stain here. So you could say this is an IHC stain, hematoxylin and DAB. Or you could also view results as a heat map. Okay, so this is something you would do after analyzing, but let's just have a look at it first. So whenever you've got analysis, you can choose any of the analysis results, and bear in mind that some modules will output results based on cell numbers, area of positivity, tissue, total tissue area. So there's quite a lot of parameters you can choose from. You can heat map across the entire array, just looking for cores that may be outliers. Okay, so they're almost the kind of side dishes. The real kind of exciting thing we're going to do is to run analysis across the array. So if you were to select all cores or maybe a selection such as this, select analyze and hit selected spots. Okay, so it's going to say 3 spots were invalid and will not be included in the analysis. It will load 111 spots into the batch processing queue, and then it'll perform some analysis. Because I'm on an algorithm that's been pre-saved, I can select this here, and you'll remember this is the one we made earlier today. I can choose to do analysis or classification. And remember we talked about how an AI classifier may be beneficial across a large TMA array because of the variability of the tissue. I could do the entire image, or I could select some annotation layers. You could put in a lot of time manually annotating. Another thing to mention is you can use classifiers to generate annotations. So that's something else which again is a high level function. We'll keep it for more advanced training, but just to allude to the possibility today that you may not have to manually annotate large numbers of cores. Okay, so we'll select this area quantification and select analyze. These jobs will be submitted to a batch process, and you should see Halo work through this one by one, analyzing cores. So they've updated the color scheme here. It used to be that translucent was cores that were yet to be analyzed. It now seems that you've got orange, green, and yellow, whereas orange is yet to be analyzed. Green is processed and ready to go, ready to be exported. And then you've got a brief incarnation of a yellow spot where that's the process being performed. As standard, Halo will perform a single cores analysis one by one. If you wanted to speed that up, you'd need to have what's called an analysis cluster, which allows you to parallel process multiple jobs at once. I think you may already have one of those, but that's something we can look into. Okay, so we don't even have to wait for this to be completed in order to have a look at the heat map. And so you can see here it's already starting to color this in for us. The result we're looking at is tissue area analyzed, but we could look at the DAB area. So this is going to give us the strongest stain cores being shown. And you can set the threshold as well. You can change these colors. There's a min and a max. This is an export in a snapshot. So you can save this as a JPEG. Usually a JPEG or PNG in Halo. Certain functions are JPEG and certain are PNG. Okay, so if I reopen the heat map, you'll see that it's progressing a little bit further. So we've got a couple of cores here which are shown in red. So the area of DAB staining is high, but we could change to look at the strong DAB areas, and obviously there's some overlap there. You can also look at the images with the markup applied. So remember we were moving through, and then you can see no markup there because it's negative. Okay, so you've successfully analyzed a TMA. The other options I talked about during the loading period was all spots for the current slide, so that will be everything, approximately 445 on this example. All spots for all slides, so if you have multiple TMAs open in the same block, then it's possible here to analyze them in almost a double batch process. Yeah, there's another option here called spot results, which will allow you to take additional options like plot spatial maps for each of the spots. But most people from this stage would want to export, so you have the options there. If you export summary data, you'll get information reflected in your CSV file or spreadsheet, one row per core. If you have object data associated with your analysis, and that typically means a cell-based assessment, then you'll have whatever this ends up being 2,000 cells per core. So you have 2,000 rows, and then another 2,000 rows for the next core. So that's the difference between object and summary data. I believe we talked about these options last time in the basic training. So let's export all slide spots. And this will bring up the export manager. And this is something as well which we talked about last time, but that gives you a few options of what you want to export. Okay, so yeah, there you can see the 111 results. You've got image data you can export. You have summary and object. Typically for TMAs, we wouldn't export object. People just want to look at the information on a per core basis, not a per cell basis. And of course, the analysis report. And there'll be one page of Excel, one page of Word document. Could be saved as a PDF, but one page of Word per result or job. So you've got here 111. So you'll have quite a substantial report if you were to export all of this. Halo allows you to export any of the input parameters as well, so classifiers, analysis settings, and annotations. Annotations are the polygons that you create when you're outlining regions of interest, typically using the pen tool or the brush tool. The classifier is something we'll come on to next, but basically it's an overview across the slide using AI to segment tissue rather than using the human eye and a manual input tool. Analysis settings are basically the settings here that you use to capture the stain. So that's more of a thresholding pixel analysis, not a complex tissue segmentation. Yeah, that's it really. You press generate and things would export into a folder. The folder can be set to the C drive or to a remote network location. Bear in mind that if you start exporting full-sized images, you can see how this then jumps up to 12.38 gigabytes for the whole TMA. So I don't know what your standard practice is, but it might be better to have that users not select full-sized and just deselect that. Yeah. There we go. Just export the thumbnails unless they really want to look at image data. You'll have all of the summary data here, which is the numerical quantitative output. Okay, so generate would start this then batch exporting data. Okay, so I'm going to stop sharing briefly just to come back to the WebEx interface. I'm going to pause for questions because we finished the TMA. And I'm just checking the chat. No one's written in the chat yet any comments about TMA. If you do have something you want to bring up, then Please unmute yourself now, and I'll try and address it. I've just heard somebody unmute. Ian. Any questions about TMA? Okay, maybe that was me unmuting by accident when I was scrolling up and down. Okay, so we'll move on to something quite exciting, which is the AI tissue classification. So let's reshare my screen. And we'll come back to the Studies tab, and we'll see that I've got an example folder here of AI. So let's select pattern recognition to start with. I'm going to open up one of our images here. Okay, what we can see is a example of a mouse ear section. So you've got skin, epidermis, dermis. I was told this is cartilage, but I'm sure with people on the line, I can be very quickly corrected, not being a pathologist by training. Then we've got these sebaceous gland examples that we want to try and segment. Now, this example first passed into my hands in 2016, and at that time, the user was manually selecting these objects, and we weren't able to use a classifier to segment them because it was an H&E image. There wasn't really a differential staining intensity between the sebaceous gland and the rest of the tissue stain profile. So let's move on, and we'll try and show the AI classifier actually segmenting these structures from an H&E image. So I'm going to move to the classifiers tab, and if anything was here, I would select new, but because this is a clean slate, we can just start from the top and work down. Random forest is the original tissue classifier. It's based on a defined feature set, and each pixel is interrogated against a set of features, essentially. It doesn't learn as effectively as a neural network. It's very fast, but it doesn't cope with variability or stain intensity differential nearly as well as the AI-based classifiers do. So let's move on to the next one, which is Halo AI VGG. So this was the initial network that we used back in 2017. It's really in there now for legacy purposes. So users who are still using the VGG network may wish to use it because it works for their application and they're happy with it. As far as we're concerned, any new user would probably move to a different network. VGG is slower, the lower resolution. It's really subpar compared to the newer networks across the board. So avoid using VGG. Next one is well, next two really are sister networks. So we've got the DenseNet AI network, and this is a network you can find in the literature. There's information regarding this network's performance and applications and so on and so forth. It's used for example data sets of say 100 plus slides where you'd fully annotate maybe 4 or 5 slides, and that would be your way of feeding data into the network. The MiniNet is actually something you won't find in the literature. That's an internal network to Indica Labs. That one is a shallower network than DenseNet. It's much faster in its training, but it won't cope with variability as well. So if you've got, say, sub 30 slides, you could fully annotate one, and that would be your starting point for the MiniNet. MiniNet will be quicker. It's almost as quick as the random forest. It's almost a replacement for the older type of machine learning. Okay, so let me select DenseNet. Anything tricky, usually select DenseNet. You'll see it says plugin here, and this is because following VGG, we realized that we could never keep up in indica with the amount of new advancements in AI-based tissue classification. So we would build an algorithm into the Halo GUI, and then by the time we released it, there'd be 10 new networks all showing different strengths and weaknesses and abilities. So we decided to configure the software with a Python plugin, so you can actually configure networks and add your own networks to Halo, and you can make the training marks through the Halo GUI, but it's essentially your network. So if you have anyone amongst you who's competent in Python, and you can use this fairly, as I understand it, basic programming language to configure networks for your use. We also have some documentation on examples of how users have been able to do this, and it'll give you almost a walkthrough guide of how to do it if you did want to add your own plugins. Okay, so let's select DenseNet, and I'm going to lower the resolution to 1. This is a bit of a trial and error process. Obviously, the higher the resolution, the longer the training will take. But if you were to come out too far, you'll see that you'd lose the detail on the structures that we're wishing to pass through the network and thus identify. So let's put it back down to 1 micron per pixel. We need to add a few classes. So if any of you have used the standard classifier, you'll recall that you can just make as many classes as you want, whatever the order you want is fine. And you make generally small training marks, 3 to 5 marks for each class, maximum of 10. This is a different way of doing things. You want a large number of annotations, and the more annotation area that's inputted into the training, the better. So it requires a longer input or time for the annotations, or working times input the regions of interest. Also, the order is important. So you generally put the most important class last, the background class first. So I could, for example, in this put the dermis, and then start with the epidermis, cartilage, sebaceous glands. Remember, in this example, the user wanted the sebaceous glands. She wanted to count them without having to manually annotate them. Okay, so you've got your classes. This is now where one would begin to label the image, for want of a better word. Now, even though I've called this dermis, I'm going to encompass some of the other layers as well. So this could be considered more of a background class. When you're inputting information like this, remember that you can use a graphical input device like a Wacom, Wacom tablet. You can draw rather than using a mouse, which I'm doing, so this might make things a little bit quicker. So because I made these classes later, the more recent classes will overlay or overlap. And this actually is a benefit to our segmentation because it allows us to make very accurate delineations between two classes. So rather than having two classes butting up next to each other, so I could, for example, draw a red outline here and have it aligning with the green. If I zoom in, I have this very accurate delineation between the epidermis and this dermis region here. I have to make sure that or I label my areas correctly, and if you remember the advice that we just discussed, if you had 100 images, you need to fully annotate 3, 4, maybe 5 of those images. So you're going to have to put in annotation time in order to get the best results. There are certain tricks, which we'll probably come on to in the advanced training, like using a classifier to already outline some of the easier layers, convert those into annotations, copy them into the classifier. But I won't go straight into that just yet. Let's just see how this analysis performs. Now notice you don't have to be 100% perfect for your annotations. I might go over the structure boundary a little bit with my blue line. When you've made some of these markups, then you can press the start training. What you'll see is it says loading plugin, and then this will then begin to show a chart. Now, one of the changes that you'll notice in 3.1 is the load plugin occurs a lot more quickly than it used to. It used to take a long time for that to initialize for the first time you ran the network when you loaded Halo. This has been improved. What you're looking for, or what you're looking at, let me do what you're looking at first, and then I'll say what the desirable outcome is. You're looking at a number of iterations that these selections are passed through the network, the layers of the neural network. This cross-entropy number, anyone who knows about entropy, is the measure of disorder within a given system. The cross-entropy is the disorder or difference between what Halo is determining to be the classes to be and what the pathologist has actually inputted. So that's considered the ground truth. So let me just make some more annotations. And here I'm just demonstrating that you can make annotations on the fly. And it's just going to feed more information to the network. And you see how the differential between what Halo is seeing and what we've marked. I can't say a pathologist is marked because I unfortunately don't have that skill set. But what the user has marked is now gone down. And that's one of your visual feedbacks. The other visual feedback is the real-time tuning window. And here you should be able to see an overlay which will modulate slightly as time progresses. And if I move around, you should see structures that have been categorized as one or more classes. So bear in mind that the recommendation here is to fully annotate 4 or 5 images. And we haven't even started on this one, but you can see that we're able to build a multi-class classifier with quite some success. And this is the unsupervised area of training. You know, we haven't actually made any annotations here. This is something that Halo hasn't seen before. There's 2 ways to improve the accuracy. The first is to make more training marks. I can't really stress that enough. If you keep adding training marks, you're going to get better results. And the second is to let this run for a longer period of time. We used to say with the VGG network that you wanted this cross-entropy to be below about 0.1. The new advice is more that you want it to stabilize at a lower figure. So obviously it doesn't have to be a particular number in mind, but as long as your trainings or your cross-entropy, which is the difference between what we're seeing and what the system is seeing, so as long as that stabilizes, then you know that it might be time to pause the training and run your analysis. What I could have done here is added a background class for the glass, and that would have enabled me to have area of glass versus area of tissue. Because I don't have that, I'll probably just draw an annotation around the tissue before I run the classifier. It has the same effect. It's just going to focus the classification onto the tissue itself. When I'm viewing my markup, I can select advanced options And under annotations, I can under the classifier options, I can convert this to annotations, which is a trick of the software, enabling you to use machine learning to very quickly generate hundreds or thousands of ROIs. Or I can change the view to a probability map. And here I'm going to look specifically at the objects that the user was interested in. So this is the sebaceous gland. And you'll see, if I resume the training, that now these areas are shown in red, being very likely to be the sebaceous gland. Let's have a look here. This is a bit more of a confusing one, so you can see it. I might have to make additional training examples here. What else? Okay, so the probability threshold, let's increase that a little bit, and you'll see now only areas where you've got this sebaceous gland likely to be present. That's the only area that's included. If you want to count the area of your class, particular class, or you want to count these as objects, then you need to make sure that this probability threshold is set. Okay, let's switch back to the alternate view, and we'll run this classifier and see how it performs. Okie dokie. So we'll pause training, and we'll select save. And this is the dense net. Again, save to study pattern recognition. We're now going to run the classifier. Because I didn't set a background, I'm going just to annotate the tissue. And this will enable me just to get an accurate estimation for the tissue area and the areas of the different classes. I don't want to count this glass as the dermis. I should have done a background class really if I wanted to do that. Another new feature of Halo 3.1 is for those users who are connecting from other countries, we now don't need a UK or US keyboard to adjust the size of this targeting reticule. That's me doing it using the hotkey, but we've built this into the software now, so it should be easier for those who've got different language settings on the keyboards. Okay, so remember last time we used the flood annotator? I've just used that to select the area of the tissue almost in its entirety. I will also shrink a little bit, pressing the Control minus, just to come in a little bit tighter. Not too much so it goes over the epidermis. And now in the classifiers tab, I'd like to run the classifier across this annotation layer. It'll prompt me to save the annotations, and it should start running. Now you'll need a GPU in order to run, train and also run an AI-based classifier. One of the advantages of the 3.1 new release is there's a GPU training coordinator, and this allows groups like yourselves, which have a Halo AI group array or multiple AI seats, to send AI jobs to machines which have the GPU parallel processing power. So you'll have the training coordinator initiating a first step of checking the local system for a GPU to see if it can be run locally, or it will then check the analysis server to see if that has a GPU which you can send the job to. So what we've struggled for a long time to be able to send GPU-based jobs around the Halo infrastructure, but we can do that now with the GPU training coordinator. Okay, so usually you see a little progress bar here, but it must have just progressed in the background. So I've got 0 active and nothing queued. If we look at job actions or filter, sorry, job status complete, you can see here that it has been completed. We can also see all of those TMA calls that we did earlier. Okay, so it says complete there. By the way, I didn't mention this last time. This is the analysis queue, and you can select jobs, change the priority of jobs that are being run, delete jobs. It's almost like a printer queue, and very similar to that function. Okay, so let's come to the results, and maybe we'll have to reopen the image. Usually you'd see the overlay already displayed. That might be something to do with 3.1, but you would see this. Yeah, it says analysis complete. So let's reopen, see if we can see some analysis. Okay. Okay, so there is our objects of interest, the sebaceous glands. If we run through, we can see a lot of objects that have been detected. The error here is obviously there's no background class. So if I was to see this again, I'd select a background class, and that'll enable us to focus more correctly on the tissue versus the background. Okay, so here, when you've done an AI-based analysis, I usually recommend having a little look through and just seeing structures like this, where on first pass you won't think it's a gland. You'll think that the system's got it wrong usually, and then you'll come in and you'll look a bit closely and realize that actually that might be something of interest, like here. That's not detected. That one is. That one is. That one is incorrect. So I'd probably suggest making a training mark over that region. Those two. That's correct. Correct. Okay, so in terms of your results, classified area, we'll ignore that for now because we've classed outside here, which is not useful. But we've got our area of sebaceous glands, and we've also got, importantly, object level data. This was a new addition to Halo 2.3, I think, where you could have object data based on the classified regions. So let's have a look at our sebaceous glands. Remember, you can filter as well, so we can look at just the sebaceous glands. We can select all of these objects by pressing Control A. And we've got information on the area, the perimeter, and an identifier for each of those objects. And this is exactly what the end user wanted from this. She didn't want to be able to have to annotate everything manually. It was just identify the structures, export them, and then have an area based on this data here. Don't forget, something new in Halo 3.1 is you can expand out the object data table. Let's go back to Halo for that. And you can make this larger. So if you have a lot of data, like you would in some of the Hyplex modules, you can view all this here. It's possible to reseat that just like so. So we're going to make a move towards making Halo more flexible, where different windows can pop out and almost have an image analysis cockpit of different different parts of the software. And this is just a small nod to that sort of development track. You know, you can pull out the object level data from this small corner where it's harder to see to a separate monitor if you want to review it. Okay, so that's examples of tissue segmentation. I think I'm going to come along and just overview some other types of deep learning networks. These are new additions to 3.1. So let's close this example and select classifier actions and new. Here we're going to clean the slate, so we've now got nothing from the previous classifier, and I'm going to open a new image where I'm just going to try and use AI to classify the nuclei. So this is an example of a tumor where stained with H&E, and you've got stromal cells proliferating, tumor infiltrating lymphocytes and the tumor mass itself. There's an array of image analysis challenges here based on the size of the nuclei and the stain intensity and so on. So what I'm going to do is come back to the classifiers tab, and we're going to demo something which is brand new to 3.1. That is the ability to segment using the nuclei first segmenter and then secondly the nuclei phenotyper. So let's select nuclear segmentation. And this one's a little bit different from the DenseNet in that, number one, it segments nuclei instead of tissue areas. So it's a different scale of focus. We're looking at a much smaller object. And number two, it's what we've termed a pre-trained classifier. So this is brand new to Indica Labs. This is an example where we fed data in from a large number of images based on ISH, H&E, IHC stains, but we can see it's a pre-trained classifier, so it's a bit different. You'll also notice when you select one of the classifiers, you'll select nuclear seg. It will automatically realize that this is a bright field image, and it'll say bright field here, BF. If this was fluorescent, it would say FL. So you only need to select nuclear segmentation, and Halo will determine which algorithm is appropriate. Okay, so yeah, it already has the classes for you. You don't need to fill those in yourself. And if you classify and open the real-time tuning window, you'll see that it is automatically finding those nuclei. This does a better job at finding them in the difficult condition. I mean, look in here. These would not be found using the traditional watershed segmentation. This is finding nuclei across difficult to analyze sections using a pre-trained set of training data. So we haven't had to mark out nuclei individually here. Okay, what you could do is you could feed in your own data. So if you wanted to add, there's the option here to outline nuclei. And if you have something which doesn't work using the pre-trained settings, then of course, then you can add them yourself. Then you can start training, and the same settings are applicable. If you want to save, you'll have to change the file name, obviously, because this is one of our pre-saved networks, part of the software itself. Okay, that was a nice easy demo because Halo did everything for me. The next thing I'm going to do is to select, I'll start new again just to remove these classes, and then I will select the nuclear phenotyper. Okay, so what we'll do is we'll first complete stage one, which is to load the segmentation. So we're going to use pre-trained data for segmentation. So I click load segmentation and I select all studies. I'm going to use the nuke seg bright field plugin. Okay, so if I zoom out, eventually the tuning window will update and you'll be able to see. I might need to press start segmentation. So we need to set the algorithm to work, and you'll see the overlay of the cells. There we go. So the white outline determines where our cells are. The next thing to do is to do part two of this process, which is to phenotype. So we're using the pre-trained data to find our nuclei. The second component is labeling them. Now, it's lucky you don't have to click on each object individually or mark it individually. You can simply add in classes like so. And what you're going to do is select a class And we've grayed out the other tools and we've left you with one. It's called the multi-select tool. I like to call it the highlighter, 'cause that's what it looks like. But essentially, again, it's got this selection window, and all you're going to do is draw an annotation like this, and everything within that is automatically fed in to the tumor cell class. Okay, so the next thing to do is to add some for other classes. Try and get these right. It's quite hard for me to determine this. Select some for immune. Remember, you can adjust the size of the brush. Having to be very careful, I don't confuse the immune and the stromal. These ones look like immune to me. Okay, so you don't really need to make a large number of selections because within each selection you're putting lots of classes. Then all you need to do is to start the training. You'll see this cross entropy decrease over time. You can classify up here like you did before. And again, it's a little bit different. It's the whole image that's going to be shown as a markup. You don't have that window like you did before. You'll see that if we move across to unseen areas, Halo will start to try and classify this is tumor, this is stroma, and where the immune cells are. And that's it really. That's nuclear phenotyping using an AI-based network. The things you have to remember are to load a segmentation, and this could be Halo's pre-canned segmentation, or it could be the ones that you've optimized yourself. And then you start the segmentation to find the cells, create some classes, and then you start training, and you'll see this overlay here showing the cells colored in different colors. Of course, if I want to classify the field of view, let me just pause the training. This is nuclear phenotyper. Okay, so you can see there, it's located the image, run the training. I might have to close this and reopen it in order to see the results. Let's check. I think I can see a markup on this field of view. Results will be shown here. Total cells, tumor cells, stromal cells, and immune cells. So obviously this is as good as the data you put into it. There's the interactive image link that shows you individual cells and what they are. Possibly this needs to be updated. These look like they're incorrectly classified. But this gives you the idea of how you would perform nuclei segmentation and phenotyping using AI. Okay, so I'm going to pause there. We've covered now AI tissue classification actually in its entirety, area detection, and also tissue microarrays. So I'll pause briefly for questions, and then we might have a small recess of 5 minutes before we move on.
Hi, I've got a few questions.
Yeah, please go ahead. I'll try and answer them.
Okay, so the first one's about the classical AI classifier. Can you put the what's more important, or what's the important point? Is it the order that you create the different classes, or is it the order that you put in the teaching examples?
The dense net classifier.
Yeah, because you know how it prioritizes the most recent one over the oldest one if you overlay them. When you say the most recent, is that when you actually, do you know how you type in all the different classes before you actually put in teaching examples? Is it taking the...
That's right, yes. It's the order of which you put in the classes. You can make annotations or selections of the ROI in any order that you want to, as long as the classes themselves. I typically put background first. If you want to do a quick analysis, you can do background and then your class of interest versus tumor, and then everything else is going to be background. So it'll be adipose tissue, infiltrating immune cells, stroma, glass, dust, debris, tissue fold. Everything else will be background. Just the tumor. That's an easier way to do it rather than having multiple classes. But in that case, the background would go first. In the case of where you've got multiple classes, and I would suggest putting the class of highest priority last. So it'll be background, then dermis, epidermis, then cartilage, then the sebaceous gland was the bit which I really wanted to identify.
Okay, that's the idea that you can dump all the background into one class is really handy because that saves a lot of time. Yeah. Second question is, if you create a kind of teaching algorithm and then you save it and then you open it again and you add more to it, instead of restart teaching, the tab changes just to start instead of restart. Does that mean that it's going back to the very beginning and starting from scratch, or is it building of what it's already been taught if you've added more examples?
Building on what is already been taught.
Right.
There's also, building on that comment, you can change your classification using the same training example. So you could switch from random forest to dense net with the same classes if you wanted. So you're building a very large repository of usually manually made annotations, so you don't really want to lose that with each change to the classifier. If you press restart the training, you'll still keep the annotations, just the classifier will then start to put that data in from the beginning. If you just press resume training or start from a classifier that you've loaded, then it will just add that data to what it's already learnt. Right. So I think is what I think you said in the second part of the question.
Yeah, so I can't remember if it gave you an option of resume or whether it just had restart whenever you reopened the classifier. It does have the option of kind of resume from where you left off if you've closed it and then reopened it.
Yeah, let's just open it and check. So it says start training. Yeah, I'd have to have the image open again. Maybe have the same image open, same classifier.
I can't actually see what you're doing. It's not on the screen at the moment.
Yeah, I'm just checking it works first, as you can imagine. Okay, I'll share the content. I wanted to know. So what you can see here is I just opened it, and I had the same image open. I loaded the dense net classifier, and it started with a cross entropy of down here.
Right. Okay.
So it didn't begin from all the way at 6 or whatever the entropy is when we first started training. So though it said start training, it's building on what it already learnt.
Okay, that's fine.
You can see that because we're already at this sort of 0.1 level.
Yeah, because the graph zooms right in, and then you lose the... When you look at it, you don't realize that actually
you lose the context. Yeah, that's a good point.
So I get a few more questions. So the next one is some tumors that I work with, or even if you've got a large set of tumors, they've got a huge variation in appearance. So, for example, neuroblastoma can be a small round blue cell tumor in some areas, and it can be like mature nerve tissue in other areas in the same tumor, never mind across lots of different tumors. And I've always kind of found it difficult when trying to teach it because what you're calling tumor looks completely different in different parts of the slide. Does it handle that well, or is there a different way you can do it? Because in the past, using simpler things rather than the AI one. I think it was Random Forest was trying to use at one point. I basically just had 3 different classes. One was well differentiated, one was poorly differentiated, for example. Does the AI handle variation in appearance across the same entity?
It should do. So the way I usually describe it is that if you can see a difference by eye, then it should be able to detect it. It's the same as with cell segmentation. If you can't see where one nuclei ends and the next begins, neither will the software. It's not going to be able to do that. Generally with AI, it can detect differences in the morphology of the differentiated tumor compartments. So I guess you've got a couple of options. One is to do your random forest style strategy where you have subclasses of tumor, which would probably work. The other is to try the AI's robustness against multiple across the having a single class across the multiple tumor types and just see if it's able to group them all. It's only something you're going to find out by testing, but we can also assist you with that testing. So if you want to send the images across, then I'm here and Natasha and Ghislaine are also on the call, which I think we've all been in touch anyway by email. But we can have a look at the image and give it our best effort as well.
Yeah, that'll be interesting to see, especially sometimes when you have like big cohorts of colorectal cancer, for example, you've got this huge range of appearance from signet ring to your classical, reasonably well differentiated one, and it's very difficult to try and catch all because they look so different. Also, another question about the nuclear segmentation. When you does it only look at the nucleus when it decides which class it's putting it in, or does it actually look at the area around the nucleus, like the cytoplasm and things like that? Or is it literally just based on the nucleus?
I had this question come up before, not long ago. I can't recall the answer. I believe it just looks at the nucleus, but I can double check that one and get back to you, Alistair.
Okay. And do you know how when you were clicking around, you managed to get a square around each detected nucleus? Is it possible to reallocate a nucleus into a different, if it's got it wrong, is it possible to just reallocate it into a different class?
No,
As
sadly
part
not.
you can't kind of go, well, that one should be in
No.
here and then just stick it in.
That
And you
was
can't.
a feature which people had requested during tissue classification. So
Yeah.
say that one of these was incorrect here that we see in front of us, could you just right click and remove it? You can't do that on the nuclear either. You couldn't do it on this and you can't do it on nuclear.
Okay, that's brilliant. That's all my questions. Thanks.
No worries. I'm just writing down your comment about nuclear compartment or cytoplasm as well. I think it's just the nucleus it looks at, but I will double check.
Very exciting functionality on the nuclear segmentation with Halo 3.1. So huge congratulations on that. Quick question on the downstream utilization of that data. Can you export? So what does the actual data output look like downstream from the nuclear AI classification?
At the moment, it's just going to be if it's finding the nucleus, it's just going to be almost like a area-based classifier with a number of objects. If it's the nuclear phenotyper, then I think we saw some examples here. The downstream is this result output where you've got percentage of the cells that correspond to individual classes across the population.
But is there any way to so when you run the regular nuclear segmentation using the watershed method in the analysis modules, and you run this at a single cell level, you get the actual coordinates of each cell, which you can then feed into downstream processing, which is a really interesting option. So is there any way to get the actual cell level data and coordinates for each cell?
Oh, sorry, this would be hopefully what you can see here, Victor.
Yeah. So that's the actual. So this is on an individual cell level.
Yeah,
And
if I,
you would be able to export
yeah,
this with the coordinates. Okay, cool.
if I scroll in and click on an object, you should see it highlighted here. There, let's find another one. Yeah, and if I click here, this is this one. So yeah, you've got individual cell level. With respect to the other algorithms, eventually there will be an option where you can load some analysis and you'll come down to, let's just choose something of interest, multiplex IHC. There will be an option here where it says nuclear detection and it will say use AI detection. That isn't in 3.1. That's something in alpha test at the moment, but eventually you'll have the ability to plug in AI-based segmentation into your normal algorithms. It'll probably roll out with multiplex IHC first and then follow on later with other ones. One thing I would caution against is creating classifier to annotation type measurements when you're using the nuclear segmenter, because you'll generate a huge data set, which will probably just lock up your hardware depending on how powerful it is. So the viewer won't be able to manipulate 200,000 objects or polygons very easily, and you'll end up with you'll just end up with a very slow process. I imagine it would take hours rather than minutes. So that would be up here under classifiers where you've got the advanced. If this was individual, say this was nuclei, you wouldn't want to select this to annotations. I mean, I don't know whether I should even draw attention to it because it's going to be something which probably should be disallowed, converting all of your nuclear mass to annotations.
Right.
Does
Thank
that
you, Sean.
answer? Yeah.
Just a quick question in terms of the rollout. So, do these additional AI modules become available with 3.1, or is that something as an extra feature?
These are all included. It's a part of our general update. So as long as you're covered by the service contract, then you get the training from myself, Natasha, and Ghislaine, all of the technical support from Billy and Mark, and then updates to the Halo software itself, but also to the individual modules. AI is termed a module, so yeah, these things here. If I go to new, it's not saved. These additions here, they're all going to be included as well. So you'll just see that this list increases. There's another one here as well, the QC slide, which is again a pre-trained network that identifies areas that are blurry. So I don't know whether it'll work here. There's a very light blur here, but if you start training, you should see the Halo try and find areas that are blurred or out of focus. So it might need some additional input here, but that's another network that's going to ship with 3.1 is the QC for slides. So if you were generating a large number of slides, then you could QC them quickly based on the area that's out of focus. Let's put a minimum object size in. Okay, any other questions?
So my colleague here, Jiqing, has a question.
Yes, thank you, Sean. I think I have a question about the AI plugin of the Halo, because sometimes I want to train some models, but maybe the model requires some very specific version of the TensorFlow or PyTorch, or even they require some third-party packages. I mean, I have a question how flexible this Halo plugin is. I mean,
I'm afraid I'm not really qualified to answer that. I can put you in touch with the AI lead developer, and I can also send across the documentation. I can send it to Victor, or if you want to send me an email, we can provide you with the documentation and then see if that answers the question. If not, we can put you in touch with the required people who actually built the plugin, so they can advise on it.
Okay, that would be great. And then maybe just one more thing. Like maybe let's say, I mean, it might not be that flexible in terms of like different versions of the deep learning models, but is that possible? Maybe let's say I just start training some model just totally outside of the halo, then I just eventually put some, just keep some like the output that's like following some format of the halos. Then do you think that would be feasible to do something like this so that the users can really like, just manipulate the output of my models, inside of the Halo environment?
So the output of the models is going to be quite consistent. You're going to get the same markup, the same training decline here, or cross-entropy decline. Output, I guess, would be area-based, object-level data. But you get the advantages, of course, you get to use all of the tools within the software to make the training regions, which would probably be quicker than if you didn't have the easy-to-access GUI. So I don't think there's a big change in the outputs or output visualization.
So as long as I just like stick to the format that Halo requires, right? I will just we can visualize the output of my trained models just as right now, or
I don't know. Difficult one to answer. I've never seen that in practice. So I guess if I find the required information, and I can also pose the question for you about outputs.
That's great. Thank you.
yeah. Thank you very much.
Thank you, Sean, for your talk. Just a quick question. The training data sets used for the deep learning classifiers, what type of tissue did it use? So was it focused predominantly on normal histology, or was any malignant tissue used?
Again, a really good question. It's brand new. I don't recall when we were informed about the networks specifically what type of tissue was used. They mentioned that it was H&E. They said a wide variety: H&E, IHC, RNA-scope data. So that would lead me to believe that tumor tissue was in there, but I can't say categorically. So that will have to be something else to put on the list to follow up. So, is there anything specific you'd like to know, or is it just whether it was malignant or?
Yes, I think that sort of feeds into Alistair's some of Alistair's questions, because I think it would be the balance between normal versus malignant.
And that is on the AI nuclear segmentation that you were interested in.
Correct. Yes. So I think
It seems to, anecdotally, it seems to pick up the tumor nuclei very well. So you would be led to believe that it's been trained on that data in order for it to pick it up straight away out of the box. But I'd happily to confirm that for you.
Yeah, because I think it also then impacts on what type of tumors we'd be looking, because there is between different types of tumors, there'll be different types of morphology as well.
Yeah.
Thanks, Sean.
No problem. Okay, so I guess we're almost at the end of the two-hour mark. So we'll probably have to pause there for today. The outlying agenda items are really the analysis using algorithms, such as the multiplex fluorescence, and also we've got the RNA scope. We've probably dealt with the bulk of the difficult topics today, particularly the AI. It's one of your most powerful tools, but it's also one of the hardest ones to get to grips with. And obviously, we had some questions about the order of the classes. So that's an example of something which needs to be really talked about in some detail before users start utilizing the system. So what I'd probably suggest is that we either bundle in the a couple of outstanding things like multiplex FL multiplex IHC and highplex FL, sorry, bundle them into the advanced training that's planned, or we can have a separate training session for that. And I'm kind of open, really. I think if Marie-Lena is online here, if she could maybe make some comments about how you'd like to proceed, whether we organise the second set in the advanced session, or whether we have a separate standalone meeting just to go through a couple of modules.
Hi, Sean. We'll have a think on that. We'll discuss it with Alistair, our pathologist in the team, and see what he thinks and how we can progress further. Either we'll have a longer session next time, which can include the modules, or we'll have a separate one, as you just mentioned.
Okay. Well,
Be in touch.
okay. Well, thanks a lot for attending then, everyone. I mean, I'm again very pleased to see everyone online today. It's really encouraging. So thank you for your attendance. We're really pleased to be able to show some of the new modules, especially the AI stuff, which has come along a long way. So we're here at your disposal, and yeah, please have a play with the system, utilize it. You've already incorporated it into your institution, so please use the existing asset you have, and we're here to help should you need any further explanation.
Thank you, Sean. If you could please forward on the video to myself, I will distribute to the list of people who have attended, and then we'll be in touch with everyone for the advanced session. In the meantime, if anyone has any questions, as Sean's mentioned, please get in touch with himself, the team, or myself if you are looking to use the Halo platform that we have with the Cancer Centre. Thank you all.
Okay. Well, thanks everyone for attending, and we'll see you next time.
Thank you, everyone. Bye.